two that mentions most probable genotype. Now, in the past, MPGs, in the past, we used to do this considerably as part of a paternity workup, a paternity study. But we have newer, obvious technologies today that are kind of a little bit better, can pinpoint a particular situation, an alleged father, so on and so forth, versus what we had in the past. But it's still relevant. In fact, students per se should really know how to work backwards from phenotype to genotype and calculate the most probable genotype. Now, table seven five, and we're going to use that in your textbook. And then two, if you go to the teaching unit in Sakai that I provide on the RE system, we are going to actually calculate through a most probable genotype, which isn't provided here in the textbook. I worked through, we're going to work through most probable genotype, and then there's a little bit of homework attached to the unit as well that should allow you to, again, practice calculating the most probable genotype. Now, looking at the table on page 155, so it gives you a breakdown of statistics thus far in retyping the white population, the African American, and the Asian population for a particular blood type, that RE blood type, that being Fisher race, we were translating that to women as well. And statistically, and running down through here, and just looking at the Caucasian population, what you see is big R1 is the most prevalent haplotype that we find in the Caucasian population at 42%. Little r is the second most popular haplotype in the Caucasian population. If you look at little r, it's 37%. And then thirdly, it's R2. R2 is 14%. And then lastly, would be big R0, which is 4. So in the Caucasian population then, in terms of most probable haplotypes, what goes, big R1 is greater than, what's next? Little r, which is greater in frequency than R2, big R2, which is greater than big R0, right? So we need that. Now looking at the black population, the African American population, okay? Big R0 in frequency is the most common haplotype, followed by little r once again. And then we're looking at big R1 and then big R2. So it's a little bit different. Frequency of occurrence in the black population is big R0, little r, then what? Big R1, and then big R2, right? And looking at the Asian population, then what do we have? The most prevalent haplotype in the Asian population is, by frequency, big R1. Okay, 70%, followed by, so Asian, it's big R1, followed by big R2, then the third most popular frequency is what? It's little r and Yeah, they're both 3%, okay? If you look, big R0 and little r are both 3%. So there's a difference in frequency in terms of a particular haplotype in a given population. And in time, you should be pretty familiar with this, okay? Now, what do we have at our disposal that would allow us to suggest a genotype? The only thing we have at our hand is serologically the phenotype. We can phenotype someone for their particular Rh antigens on their red cells. So how do we do that? Well, we take antiserum, take anti-big D, anti-big C, anti-big E, anti-little c, anti-little e, and then we find out if that red cell is positive or negative. Does that red cell glutamate or not? From calculating or from serologically testing and finding out what one's phenotype actually is, we can work backwards from that information to kind of calculate the genotype given these frequencies in this table. Now, how do we do that? Do you have your, anybody have that? Because I didn't bring extra copies. Do you have your unit on the RHs? If you look at page 4, we'll work through a couple of examples here. RH teaching unit, page 4. And I give you an example. It's like doing an ABO, typing somebody's, looking for somebody's A antigen or B antigen or neither. We do the same thing with the RHs. We have the bodily anti-big D, obviously bodily anti-big C as an antibody, anti-big E, anti-little c, and anti-little e. So phenotypically, in the example that I give you in the book, I said, let me get this right. How was that? Okay. So we phenotype somebody's red blood cells, washed red blood cells. And with anti-big D, we found that our patient's red cells were positive, okay? We do the same thing. We have a bottle of anti-big C. We have a bottle of anti-big E. And what did I give you? Okay, big C is positive. Big E, anti-big E was negative. Okay, anti-little c and anti-little e, what did I give you? Okay, these are both positive. Okay? So we phenotyped somebody. And we found they were D pos, but 2 C pos, E neg, little c and little e pos. That's phenotype. Now, in talking about one's genotype and what was actually inherited, well, D pos, correct? Okay, what we don't know is if, and we don't have anti-little d, there's no anti-little d. So we don't know if this person is actually homozygous or heterozygous for big D. This is all the information we have serologically in a test tube. Again, we don't know if they're big D homozygous or big D heterozygous. So we have a couple of possibilities. They could be homozygous or they can be heterozygous, right? Looking at the rest of this information that we have, is my patient homozygous or heterozygous for big C? Let's take D first, let's look at C second, and let's look at E third. Just look at C, only C. Anti-big C was positive. Anti-little c was positive. So is my patient homozygous or heterozygous for big C? Homo? because you have this. Your patient's both serologically positive for big C and little c, so therefore, they must be genotypically heterozygous for each of those. So big C, little c, big C, little c. Now, what we don't know, say this is mom and this is dad. This is mom and this is dad. What we don't know, no, I shouldn't have said that yet. What we don't know is, does the little c ride with the big D? Okay, in other words, which haplotype did we inherit? Could it be this? And it's particularly important over here. So we have those four possibilities. Does that make sense? We don't know which gene these particular, we don't know which chromosome these particular genes reside. Okay. What can we say then about E?
Homozygous little e,
Homozygous little e. Why?
because
You're
big
right,
E
Kels, why?
Big E is negative.
Yeah, you're negative here. Phenotypically, you're negative here. You're positive here. So that is serologic evidence that my person has to be homozygous little e. So the little e goes everywhere. Okay. Now you look for duplicates. Do we have duplicates anywhere? We have big D, big C, little e. Big D, big C, little e. Big D, what was it? Big C, little e. And looking at the genotype, okay? Can I erase any one of these? I only want one possibility. I don't want two or three possibilities of the same haplotype. Okay, let's get rid of duplicates. So what's a duplicate here? Can I get rid of anything? Can I drop anything? Look at page 6. Which is essentially the same thing I have up here. Do I have any duplicates?
Big D, big C, little e.
And where? Where?
So it'll be the first one.
Big C, big D, big C, little e. And it's, let me put it this way, do I have any genotypes that are identical? Not just a haplotype, but a genotype.
Well, the top and the bottom are basically the same, you just flip. Would that be?
Yeah, big D, big C, little e, big D, big C, little e, big D, little c, little e, big D, little c, little e. So I can get rid of one of these. Ah, there it is. It's identical, right? The genotype is identical. Let's get rid of it. We don't need it. So that leaves us with 3 possibilities. Are there any other that are identical? No, they're all different, right? Now you go back to the frequency table, okay? And what's the frequency, let's assume my patient's Caucasian. What's the frequency of occurrence in the Caucasian population of this haplotype? Big D, big C, little e.
42.
What's the frequency of occurrence of this haplotype in the Caucasian population? Big D, little c, little e.
4%?
Kels?
4.
Okay. Now, what's the frequency of occurrence in the Caucasian population of big D, big C, little e? We already had it up here. What's the frequency of occurrence in the Caucasian population of just little c, little e? Dine.
37. 37.
What's the frequency of occurrence of big D, little c, little e?
4.
What's the frequency of occurrence of Dine, big C, little e? 2. Now you just add these up. Has a frequency of occurrence of 6%. Has a frequency of occurrence of what? 79? Right? 79%. Frequency of occurrence of this genotype?
46.
46. So what's our most probable genotype in this patient? Yeah, it's this one, right? Yeah, so I've calculated, given this individual's serotyping or phenotyping, much like doing an anti-A or an anti-B, but in this case, we've worked up these particular genes and the frequency of occurrence of the various haplotypes, and all you do is add them up. So my patient's probably can't say for sure. All I can say is this is the most probable genotype. My patient is most likely this particular genotype. Okay? Sometimes, rarely, sometimes we need to do this. It might help us find and select particular units for transfusion. So, in this handout, I've given you an additional exercise or two, which I would like you to go through and calculate then a most probable genotype. You have all the tools, okay? Phenotypically type someone for the entire RH, well, big 5, I should say. The big 5 RH antigens, then based on this table, most frequent haplotypes, in particular population, you can calculate then the most probable genotype. Okay? Pretty easy. Just start out with the D's first. D positive, D negative. Go to the C's. Look at the C's, big C, little c, and then the E's, big E, little e. You should be able to figure it out. Okay. So, any questions so far? Okay, and touching up, reading this. The next tidbit of information I'm going to go over is on page 163. Okay, this is important. Well, I'm making this important. This is not, there's nothing that's not important, but maybe. When we do our big D typings, okay, you may get false positives and you may get false negatives. You've got to be able to reason through if you are suspicious that you have a false positive D or a false negative D. So let's look at the false positive listing first. Self-suspension is too heavy. And this goes to, let me ask you in immunology, have you yet talked about the primary response, that being IgM, and the secondary response being IgG, and the anamnestic response that may occur, yes, no, okay. And in order to avoid all of that, we want to operate in a zone of equivalence. Have you talked in detail about, okay, all of you are saying yes, so you know what the zone of equivalence is. It's so important for banking. And one of the things we do to make sure we're continually and constantly operating in the zone of equivalence is, given our red blood cell suspension, work with a 2 to 5% suspension on my patient red blood cells. That should guarantee that you're operating in the zone of equivalence, and to the number of drops that you place in the test tube of both cells and a serum. Okay? So if your suspension is too heavy, is that prosenting or posenting? If my red cell suspension is too heavy, in other words, too much antigen, given the quantity of antibody, where am I? Suspension is too heavy. Obviously I'm not operating in the zone of equivalence. There's a nice illustration in your book as well that should confirm what you have in your immunology book, but
If antigen is posted.
yes. Okay. So all you have to do is make sure you readjust your suspension so that, again, you're back into the zone of equivalence. Okay. Cold agglutinins. Now that goes to those tests that you do at room temperature, not at 37, but room temp and below. Okay. Agglutinins means antibody. Agglutinogens means antigen. But cold agglutinins means antibody. That means antibodies are coating or interfering with your suspensions or tests that you use that have need an appropriate suspension. And they're what kind of immunoglobulin type are they? IgA, IgD, IgE, IgG, IgM? Cold agglutinins. Cold antibodies. IgMs, okay? So you need to remember that IgMs, we refer to as being cold because they'll demonstrate themselves at temperatures below 37, below body temperature, okay? IgGs, we classify as warm because they will present at 37. They will present at colder temperatures. They need 37 degree temperature in order to show agglutination. So IgMs are cold, IgGs are warm. So cold agglutinins, if there's a lot of them, a lot of IgM type antibodies, they can coat red blood cells, particularly at room temp, okay? And what do we have to do? We've got to get rid of them. We're not going to get a typical ABO typing. We're going to come up with a discrepancy, okay, if I have a lot of cold agglutinins that are demonstrating at room temp. Would they interfere, by the way, with the reverse or the forward? Antibodies.
Forward.
They're in the plasma. Okay, they're floating around in blood plasma. You throw reagent cells, A1 and B cells, into the plasma with a bunch of cold agglutinins, and you're doing it at room temp. It's going to interfere with the reverse. Okay. So we're going to wash with warm saline and try to retight it when the cells are warm. Okay. 3, test incubation is too long. Yes. Okay. The test incubator is too long. There can be a drying phenomenon if you cook them too long, like cooking an egg. You don't want to cook it too long. And what you need to do is then just start all over again. Just start all over again, if that's the reason for your false positives. You know what Rouleau is. I'm not going to go into that. You know what Rouleau is. We have a saline replacement test that you use for reload, okay? Fibrin, same thing. Fibrin can interfere, so you want to wash. Number 6, contaminating low incident antibody and reagents. Yes, now remember, yes, we use lots of bottles of antiserum, including anti-A and anti-B. The manufacturers do not test these antiserum reagents for all antibodies. Okay, they could be contaminated, particularly the low incident types of antibodies, the low frequency types of antibodies. That would cost too much, so they don't test for additional antibodies that could react at a particular temperature. So that they can be, and sometimes are contaminated with low frequency antibodies. So what's the alternative? What do? Try another manufacturers, okay? Polyagglutination I'm gonna go into later, okay? Polyagglutination I'm gonna talk about a little bit later in the course. Bacterial contamination of your reagent vials. I will expect you at the bench, when you're handling these blood bank reagents, and they cost a whole lot of money, not to contaminate them, okay? That means you handle the eyedropper as aseptically as possible. You never touch the eyedropper to the rim of the bottle. You go down the center and out, down and up and down, out of the center, and the same with your test tubes. When you add drops to your test tube, don't touch the rim, don't contaminate the eyedropper, therefore it should not contaminate the reagent when you put the eyedropper back into the reagent. So contamination could be a big issue. Incorrect reagent selection, I see all the time. Students argue with me, I know I added it, I know I added it, I know I added it. I'll come back and say, no you didn't, because I was watching. Okay? You forgot to add a particular reagent. Centrifugation too long. Just from the pure physical force of centrifugation at our particular speed, the purpose is to drive the antigen and the antibody close together, to allow them to grab onto each other and then agglutinate. Well, if you centrifuge too long, you're going to force that to happen based on centrifugal force only. Okay, it doesn't mean it's true aggregation or true agglutination. It is not. It's because of the centrifuge going too long. Okay, so we need to follow directions exactly as to centrifugal revolutions, and that's indicated in the insert. And then the RPMs are too high, that would give you the same thing. False positives, false positive agglutination, now false negatives, okay? Immunoglobulins coating the cells in vivo. Okay, in vivo versus in vitro. Which one's inside the body, which one's outside the body? In vivo's inside. In vitro means outside, okay? In vivo, inside. So think about that. You have red cells in circulation, but for some reason being coated with antibodies while they're in circulation in your bloodstream. Okay, that will give you a positive DAT. Any situation that coats red blood cells in vivo will provide you with a positive DAT. Okay? How do we correct if we assume it's a false negative? How do we correct? Using saline activated typing reagents. Our typing reagents have a different matrix. Depends on what you buy. Some of the antigens, antibodies are suspended in saline. Some of the antibodies are suspended in low proteinaceous materials. Some of the antibodies are suspended in a high proteinaceous material. So you have to know what types of reagents you're using.
Oh,
Hello. Is it windy outside?
no.
The lights could be on the
Are they on a timer? Yeah, I guess they are. So we need to know, and as I'm charging you with the responsibility of knowing whether you're using saline-based reagents low proteinaceous-based reagents or high protein-based reagents. Because in certain situations, by the way, we run controls, particularly in low protein and high protein, we need to run a proteinaceous control. If they're saline-based, we typically do not, okay? Well, we do. Okay, let me explain that. That's the first time that's ever happened. Okay, we'll go back to ABOs, all right? Forward. What reagents do we use? Right, correct? Reverse. What reagents do we use? A1 cells are not subgroups. It's not an A2, it's not an A3, it's not an AM. These are A1 cells and these cells. Okay. Let's do this once again. Patients in AB. What are we going to get here?
1 plus.
Okay. Patient is, now we're talking about N's here. What it? Okay, what am I going to get here? Might as well finish it.
Negative.
Okay, and then my patient is your patient is a B.
No urination with A, and then urination would be negative. So, urination with A1. And then it would be some.
Patient's an O.
0, 2 and 2, over. And then 4 plus.
Which one didn't I give you? A. Oh, yeah.
4 plus. Negative. Negative, and 4 plus.
See, that wasn't hard at all, was it? We struggled for a couple of days. Okay, now, if I have proteinaceous based, let me first say this. If it's saline-based stuff, then I do not typically run an RH control. If it's saline-based, okay? If it's not, if it's a proteinaceous type of reagent, then you must run a control. Now, how do we make that? The control is usually 6% albumin. Okay? We purchase and use as a potentiator, you remember the potentiators we listed, LISS, albumin, enzymes, HG. You remember that list we went over, potentiators? One of those is 22% albumin. We don't buy 6%. We make this RH control material up from the 22%. 22% bovine albumin is a potentiator, right? Okay, so we'll make our RH control from our 22%. It should be around 6%. How are you going to calculate, how are you going to make up your 6% from 22%? What's the formula? Just give me a formula. What do I have? I have at my fingertips a 22% solution of albumin. I have to go from here to 6%. How am I going to do that? Okay, all of those hours you spent making up chemical solutions. Well, this is based on 100 cc's, right? A percent solution is always 100 cc's. How about this? volume, concentration, what I have, what I want. Would that do it?
I'm sure it was.
I wouldn't have given it to you. And yes, that's the formula we want to use. Volume, one reagent equals the other. Volume would always be 100%. Okay, and then we're going to change your concentration to a point value. Okay, getting back to this. You always run, if I'm using proteinaceous-based reagents, okay, then I must run an RH control, particularly in this case, right? If I'm not using proteinaceous-based antiserums, then I don't need to run a control, but I already have. And this is the reason. This is saline-based. This is saline-based, okay? We make the assumption that this becomes our control, okay? If my person's what's this type? A B. So if my person's a B, then we use this, you should get a negative here. We use this negative test tube as our control, okay? That means if my person's an A, I have a control. If my person's an O, I actually have two controls, okay? What am I gonna do with my AB? I don't have a control.
Would you be able to use the A1 cells and the B cells?
Good question, but no. This is the one you have to make up. You'll have to make up a control if my patient is, I could have anti-D here. If my patient's an AB pause, I still have no control. Okay? If my patient's an AB neg, then I do have a control. Right? And those are rare squared. So if you find your patient to be AB, just go ahead and set up another tube, another control, okay? Set up a control. That's kind of technically expected that you know that. And we'll do it without being told to do it. Now getting back to this listing. Okay. So immunoglobulin we were talking about, you should expect a DA positive DAT there. Saline suspended cells, only in slide, if you use a slide, you might get a negative, use unwashed cells. Then let me say this, some blood banks, depending on the philosophy of the supervisor, will indeed have you wash your red blood cells before you do any testing. Okay, that's me. Other supervisors will say, don't wash your cells at all, just go ahead and start doing the fluids and reverses. Okay? I like to bypass all these necessary washing steps in various situations, like having to wash your cells in these particular cases. So I pre-wash and then test. Some people will test and get unexpected outcomes, and then you have to go back and wash. So you'll be able to recognize what I'm talking about tomorrow, by the way. Tomorrow's our first laboratory. Okay. We're gonna learn to wash cells tomorrow. And wash cells appropriately tomorrow, which is not as easy as you think. Okay, number 4, number 4, omission of reagents. You might do that, Cummings and Mornings. Resuspension is too vigorous. Don't manhandle your buttons in the bottom of your test tubes. You kind of have to do it, not too gingerly, but not manhandle it either. You need to find that Goldilocks shake, rattle, and roll technique that'll allow you to remove the button from the bottom of the tube completely and then call whether you have a positive or negative agglutination. Incorrect reagent selection, that's always a possibility. Variant antigen, refer to the sample for further investigation. You might have 2 or 3 strange types of antigens. Reagent deterioration, I've already mentioned that, that's always a possibility. Do not contaminate these reagents. Incorrect reagent selection, yes, that's going to happen to you. Centrifugation is too short, in that you don't get a nice button in the bottom of your tube. And then RPMs are too low, which goes to centrifugation as well. So there's lots of reasons, technically, that you can have false positives. There's a lot of reasons, technically, you can have false negatives. Don't make the assumption, because everything looks good, that you're coming up with the right type of your technique. We'll assume that your technique was adequate in 90% of the time, about 90% of the time. Okay, couple of things. Do the RH antibodies, C, D, E, et cetera, bind complement? The answer is no. What?
That's what I thought you said.
Yes, I did say I would. The RHs do not bind complement, that's an important fact, okay? That means that if they are involved in a transfusion reaction, then the breaking down of the red cells are going to occur extravascularly, okay? Complement's not in the mix, and they typically are not with RH antibodies. The complement is not bound by RH antibodies, then if there happens to be a transfusion reaction of some sort, then the destruction of the red blood cells will be extravascular, okay? Extravascular. 2, going back to the anamnestic response, so I don't know what these guys called it in immunology, primary, secondary, and IgM, IgG. If this person has been previously sensitized to a particular antigen by either transfusions or pregnancy, previous transfusion or pregnancy, and by the way, those are the only 2 routes that we can become sensitized to a particular foreign antigen, is by previous donor cells, therefore antigens, foreign antigens, or in females' pregnancies. Why? Because we know some red cells can cross the placenta from the baby to the mom. So men, it has to be a previous transfusion, obviously. Okay. With women, it's either of those 2 routes that we can become sensitized. Okay. Now, assuming that we are and have had a couple of transfusions many moons ago, many years ago, and assuming too there were some foreign antigens on those donated or donor red blood cells, then our immune system would do what? Once it realizes that this red cell that was given to me has foreign material or foreign antigen on it, my immune system is going to do what? Begin to make an antibody to those foreign antigens, right? Make a primary, you'll have a primary response. And that primary response is an IgM type code. Okay? In time, that antibody titer is going to fall off. Not that there's a lack of memory cells. Okay? Some of our plasma cells have learned to make an antibody to a foreign antigen. And that program of making this antibody is passed from one generation of B cells to another generation of B cells to another generation of B cells, and so on and so forth. Okay? We may not be able to pick that up serologically, given our procedures in blood banking at the bench. The problem's going to lie in that if we read, okay, expose this particular patient I'm describing to that same, has to be identical, to that same antigen, okay, then we're gonna have an anamnestic response. The word anamnestic means what? Or secondary, you might have called it a secondary response. Anamnestic means memory, okay? And that anamnestic response is going to be of the IgG type. That can occur within anywhere from 1 day up to about a week. That's re-exposure to a foreign antigen. So a transfusion reaction can happen the day that within 15 minutes, a particular red blood cell being infused, given that I was previously sensitized, okay, and I can have an immediate transfusion reaction. And that can still occur anywhere from 15 minutes up to 7 days, okay? If I haven't been sensitized, if the patient has not been sensitized, okay, it's not an anamnestic response, then it is a primary response, and it can take anywhere from 10 to 14 days for an individual to show a reaction once they've been exposed to a totally new type of foreign antigen. Now, part of the workup of transfusion reactions, again, is the DAT. Okay. Typically, the DAT will be positive. And we'll come back to that. The DAT will be positive. And the antibody screen that you do secondarily may not be positive. You can have a positive DAT and a negative screen, or you can have a positive DAT and a positive screen, okay? And you'll see that in various cases as we go along. But I wanted to point out that we have to be concerned as to whether we're dealing with a case that's an anamnestic or a case that's a primary, okay? Now, other points I want to make. Okay. In the last 2 or 3 pages in this chapter go to RH antigens, other than what we've been talking about up to this point. There are some individuals that are called RH null. RH null means an absence of these, well, let me say this, an absence of all RH antigens, okay? They have no D, they have no C, they have no E, they have no little c, and on and on and on. So an RH null individual is an absence of RH antigens. Now, the genes can be amorphic, meaning that they reside on the chromosomes, but they're not active, they don't produce a product, okay? Or, the second scenario is they could be regulatory. And if you read on the bottom of page 164, the paragraph or 2 that describes RH null, see it's inherited in 2 ways, as to either a morphic situation, okay, or a regulatory situation. In any case, we have either no RH antigens at all, RH null, or there's a subcategory called RH modified. There could be a little bit of antigen qualitatively on the surface of the cells. So they call it RH modified, if you would. Additionally, unusual phenotypes. CW, I mentioned CW before. People that are CW positive or CW negative, what's the frequency? We used to think, and go back to an older edition in the book, you'll find that it indicates that CW is allelic to big C and little c. That's not true. We know now it's a separate gene on a separate chromosome not related to big C, not related to little c, okay? Now, what's the frequency occurrence of little c in the Caucasian population? Look in front of your book. How many of us running around out there are CW positive? What's the frequency of occurrence of CW? It is in the RH system.
None.
Yes. Some books will say a little bit less than one. Some books will say a little more than one, so in around one. What's odd about this, and by the way, what's odd about this valley, let me say this, is there seems to be a lot of people in the Weirton area that are CW positive. I have no idea why. They've statistically done a study, and I think they've come up with about 25% on average. People that live in Weirton are CW positive, which is strange and weird, because the frequency across the country is less than 1 or less. Therefore, anti-CWs are not found frequently either. If you think about it, if statistically on a red blood cell that could be transfused, it could be 1 or 2, could be CW negative. If you transfuse those, it's very unlikely that anybody's going to make an anti-CW. That's not true in Weirton. I don't know why. They have lots of CWs. And they buy the ants there at Weirton Training Center because of that fact. And it's expensive because it's hard to make antigens to CW antigens. Anyhow, it seems that this particular antigen can occur, again, it could be allelic, we don't think so. It could be, we think it could be inherited, and it just happens that way back when people populated Weirton, they were carrying that particular gene, and now everybody up there has it. And I don't know. We really don't know why. Okay. The other one I want to mention is F. Okay. F is a combination antigen. It usually represents a combination of little c and little e together, okay? Both little c and little e are represented. But it has to be on these two antigens have to be from the same haplotype, okay? From the same haplotype. And we will test for F all the time when we get in deeper into our laboratories. So I wanted to mention little f, yes, little, as a combination little c and little e, as long as it's on those two genes are on the same haplotype. Then we get into G. Okay, G is an antigen as well. Most people that are big D positive are also big G positive. So most people that are big D, RH positive, big D, are also big G positive, but all people that are big C positive are big G positive, okay? So most Ds, but all big Cs are positive for the big G antigen. And I'm just reciting a few facts here. All right, what else would I want you to know? So read through the rest of these. Oh, concentrate on big B and VS2. Okay? Big B as in victory and VS. It goes to race. People that are big B positive and VS positive are generally of African descent. Caucasians are generally native for both of these, generally native for both of these, okay? So we see more of these individuals, BBS, in the African American population in the U.S. Okay. One other fact. There are those individuals out there that do not have the genes for C, E, okay, little c or little e. All of they have are genes for D. Okay? We kind of call these people, they have a variety of names. We call them super Ds, okay? And typically, in the textbook, they're written a number of ways. On just big D, the absence of C, the absence of E, or it could be written like this, okay? In terms of a haplotype, and they have no big C, no big E. And there is a paragraph or two that addresses the super D people. Okay? Kind of interesting to work with those and type those. Okay? So either a dashed line or a couple of dots usually mean that they're super D people and they have neither the C or the E. Okay. If you look at the cases at the end of this chapter, and we will soon be doing these. And this goes to antibody identification. First antibody recognition, then identification and isolation. And Kels, you looked at what? Two?
ABO grouping, it was a two-part.
Oh, it was two parts?
Yeah.
Oh, okay. Don't forget, revisit the blood bank guide. Okay? I think what you get from me and you get from him, you'll probably truly understand the concept. All right? Okay, one of the things we do, now I gave you a key sheet that represented a panel of 11 donor cells. Okay. When we want to do a quick and dirty screen, we don't do those 11 cells, we do 2 or 3.
I don't know who that was.
I think that was our secretary. Okay, we do a 2 or 3 cell screen. Now, looking at case 7.1 in your book, on page 167. Just to read this, 2 units of blood are ordered on an 89-year-old woman with myelodysplastic syndromes. Okay? So what is myelodysplastic? Moving into possibly leukemias, right? Okay, she had been transfused 3 years ago, and she had 6 children. That's 80, she's 80. So given that she had 6 children several years ago, she was probably sensitized somehow, somewhere with these fetal cells. Routine pre-transfusion testing showed, first of all, her forward and reverse. So what is she forwarding as? And neg, and what's she reversing as? So are you happy with the forward and reverse? Is there anything that bothers you about the forward and reverse? Yay, good. Okay. So the order typically is group, type, and screen. When you see that, then you have to screen for antibodies. Okay? And typically it's either 2 cells or 3 cells. And in this case, they're offering you a 3-cell screen. And the 3 cells are big R1, big R1, big R2, big R2, little r, little r. Okay? And of course with genotypes. Now, the zeros mean that the manufacturer has tested that particular cell for that particular antigen and found it to be negative. The plus sign means that the manufacturer has tested that particular screen cell for that particular antigen and has found it to be positive. Okay? So your first cell there, big R1, big R1. They found it antigenically to be big D positive, which they should. Big C positive. Big E negative. Little c negative. Little e positive, antigenically little e positive. Little f negative. Now M negative and positive carries the antigen big N. And doesn't carry the antigen big S. Does carry the antigen little s. And then you can see P1, tested that R1, R sub, big R1 for P1, found it to be positive. Lewis A negative, Lewis B positive, big K negative, big K, little k positive, Duffy A negative, antigenically Duffy B positive, antigenically JKA negative, which is a kid, antigenically JKB positive, right? So what they've done, and you could then interpret what I just said and apply it to the big R2, and then little r. Of course, your little r should be, that cell should be D negative, which it is, right? Now what we do, and I'm only gonna put a few up here. Now, of course, this particular case is given to you in gel, which we'll do later in the semester. Okay. So I have a big R1 cell. Okay, D, C, E, little c, little e, and it was positive, right? Translate this to Fisher rays, Wiener to Fisher rays, which is what's been done right here. 1 means big C, positive, which implies what about big E?
Negative.
Negative. Okay? So far, so good. What about little c, little e?
Positive little e,
Positive little e,
negative little c.
and why?
Doesn't 2 mean positive big E and little c? And 1 means
You mean
positive.
if I had this else?
Yeah,
Okay,
and then 1 is positive big C little e.
yeah. This implies big E pos, right? Which also means that big C will be negative, big R goes to D, okay? And then what can we say about here?
Positive little c, negative little e.
Okay, we'll go with that. Now what we do, these are already 2 to 5% suspensions. These are reagent cells. They're already 2 to 5% suspension. Now what we're going to do, we're going to do an immediate spin phase. We're going to do a 37 with some sort of potentiator, either albumin or LISS. Okay? We're going to include an anti-human globulin step. And then lastly, we're going to include a Coombs controlled check cell, which is a control on that phase and that phase only. Okay? We're going to look at the reactivity we get. If, for instance, I get nothing here, it's something like that, there's my tube testing. So this takes into account patient plasma. We use patient plasma, which means we're searching for unexpected antibodies, okay? These cells, let me say this, every one of these cells, whether we're looking at the 3-cell screen, the 2-cell screen, or the 11 cells, will always be and must be O type. these are all O's. If we were to group and type them, they are all O's. Why? We know that A cells carry the A antigen. We know that B cells carry the B antigen. We know that ABs carry both A and B antigen. Now remember, you take patient plasma. We've already done their group and type. We're not interested in identifying anti-A, anti-B, anti-A comma B. We don't want to identify that. Let's get rid of that concept by using O cells and O cells only. O cells that are negative for the A antigen, O cells that are negative for the B antigen, okay? If I did use, for instance, if the cell was an A, when I mix, let me erase. Okay, so if my patient was indeed an A, okay, I know that in his serum has a naturally occurring anti-B, right? Right? Wrong? This is plasma. If my patient was typed as an A, what naturally occurring antibodies are in his or her plasma? Okay. So if this is an A cell, and I get a agglutination, what have I probably identified? I've probably identified this, which I already have, by doing the forward and reverse. Making sense? So let's not use A cells. Let's not use B cells. Let's not use AB cells. Let's just make all of our panel cells suspensions of O cells and O cells only. Why? Because they don't have the A antigen, they don't have the B antigen, okay? Therefore, I would not identify an anti-B using my patient's plasma. I won't identify anti-A using my patient's plasma, okay? You get it? So all your panel cells, again, whether they're screening cells, panel cells, should be of O type. Now they'll have other antigens, but they won't have the A antigen, they won't have the B antigen. They'll have other antigens, sure. And those other antigens are represented here by the company serologically testing them for. Okay, looking at this big R1 cell, the company tested it for the antigen little k. Okay, are you with me? I'm going to squeeze in a few here. Little c, little e, I could put in Duffy A, big count. Okay, so the company has tested this O cell, that's big R1, big R1, for additional antigens that are listed across the top of the key sheet. Okay, so this patient was Kel negative, and meaning no Kel antigens, and one about Duffy. Duffy A was negative as well. Okay, meaning that this cell had no Duffy A antigen, had no big K antigen, was little k positive, carrying that antigen, and was also what? Duffy B. Okay, carrying the Duffy B antigen. Are you following?
Sort of.
This is all laid out for you. Okay? All you have to do is interpret it. The company has tested these respective cells for additional antigens. In fact, it's tested the R1 cell for all of these antigens that are listed across the top of this key sheet. And either the antigens are there or they're not there. If they're on the red cell, they indicate that with a positive sign. If they're not there, on that red cell, they indicate that by a 0, representing the negative sign. Okay? Then what we do is we take these cells and we do an immediate spin or room temp. We take patient's plasma only, and mix it with this cell. We take a drop of patient plasma and mix it with this cell. We take a drop of plasma and mix it with this cell. All right? And we spin it real quickly, down 15 seconds. And we pull out the test tube and we read for agglutination. Now, let me do this. Oh, I already have one up there. I don't want to confuse you more. Now, what we do, okay, we're needing to discover whether the patient has an unexpected antibody that had to have been materialized either through previous transfusions or if it's a woman transfusion and pregnancy. And she was immune stimulated. We look for, and we go down the list, look at our reactivity. We look for a cell that's completely negative in all phases. Completely negative in all phases. Then we come back. And what this is telling me is, okay, in my patient's plasma, there is not an antibody that will react with these antigens. I'll just put this up here, okay? There's not an antibody in my patient's plasma that when mixed with these red cells would not react with these antigens. So I can come back and I just cross those off. All right? I know I have an antibody here. An antibody that's reacting with whatever antigens are on this cell. I'll make up a few here. I'll make this new. Okay? Just for the heck of it. There's something here. Has to be an antibody reacting with an antigen on this cell. All right? So, now we make an interpretation. Is it cold? Is it an IgM that would demonstrate at a colder temperature, immediate spin, or is it a warm? Is it an IgG? Well, this is looking to me like it's an IgG. Okay? Because it's reacting where? Starting to come down at 37. And it's even more strong at AHG, anti-human globulin. Right? So with that in mind, and I do what this is called a process of elimination. I go back and I can look at this cell and see which cells are positive, okay? And I don't have 11 or 12 cells here. By the process of elimination and looking at what antigens I eliminated, okay? And looking at this, and looking at this, I know it's not this because I've already crossed it out, it didn't react here, all right? This could be a CAL, an anti-CAL, it could be an anti-WA, or it could be an anti-Big E, okay? Whatever's in here, agglutination, is reacting with either this antigen, or that antigen. Am I making sense? Yes, no? But we will have many more cells, and by the time we do go through this process of elimination, looking at all negative cells first, crossing off all antigens that remain on that cell. Okay? And looking at then, interpreting then only those that are positive, we can eventually conclude as to what antibody, unexpected antibody, clinically significant antibody is represented here. Now, we're only getting started, okay? This can get a little complicated at times. And we're going to do this a number of times in the lab. We're going to talk about a number of situations in here. I'm going to give you dry cases, wet cases, and then eventually, I think you'll have it. It will take some time. You just have to work at it, all right? So looking at this screen, what you want to do, and they're only giving you one phase here, gel. They're not showing you immediate spin, they're not showing you 37, they're not showing you HG. They're only giving you gel, and it's an indirect antiglobulin test, not a direct. This is all indirect antiglobulin, it's not a direct. We can begin the process of elimination. Okay, so let's look at the screening cell first. R1, R1, R2, R2, little r. Now, I have with a big R1 cell in gel at 2+. I have a big R2 gel 2+. But I have a little r cell that's showing that no agglutination in gel whatsoever. So I want to take that cell, and that cell by itself, that cell alone, and if you have a pencil, I don't, does anybody need a pencil? A pencil? Yeah. I want you to take that cell, with that cell only, and go back to the extreme left, okay, and cross off all the antigens that are represented on this little r cell. Little r, negative for the D antigen. Little r, negative for the C antigen. Little r, negative for the E antigen. Is positive for little c, cross that. Is positive for little e, cross that. F, crossed out. M, crossed out. S, big S, crossed out. P1, you can cross that out. Lewis B, you can cross that out. Big K, you can cross that out. Little k, you can cross that out. Duffy A, you can cross that out. JKA and JKB, you can cross both of those out. Okay, that leaves us with what possibilities that might explain the 2+ that we're getting in gel with the R1, R1, and the 2+ that we're getting with the R2, R2. Okay? So by doing that, what remains as possibilities? Well, you got rid of the C, you got rid of the little e, you got rid of the little f, you got rid of M, you got rid of big S, you got rid of P1, you eliminated Lewis B, you eliminated big K, little k, Duffy A, you eliminated JK and JKB. So that leaves what? Big C, you did not cross off. Big E, you did not cross off. So you want to circle those for consideration. Looking through, then, what do we have left? N is a possibility, big N, you did not eliminate that. Little s is a possibility, you want to circle that. Okay? Lewis A is a possibility, you want to circle that. Duffy B is a possibility, you want to circle that. So what possibilities do we have remaining after our initial elimination? Big C, big E, big N, little s, Lewis A, and Duffy B are all still in the running as possible antibodies. All right? So I know my screen was positive. I know I'm picking up something. Whenever your screen is positive, then you complete an additional 11 cells, which is given to you below. Okay? You do the same thing under gel in the indirect antiglobulin test. Slide down to cells 1, 2, 3, Cells 5, 6, 7, 8, you see those, and they're all negative. No agglutination. In IAT, 5, 6, 7, and 8 were all negative, right? No agglutination. Okay. You can take a straight edge. And maybe you need to do that. Take cell 5, just cell 5, ignore 1 through 4, because they were positive. Take cell 5 and do exactly what we did. Okay, cell 5, go back and cross off all the antigens that are residing on that particular cell. Cross off all the positive signs on that particular cell and that cell only. Okay? Then after you've done that, slide down to the next cell. Cell number 6, which is also negative. Okay? Now take your straight edge or whatever and cross off all the antigens that reside on cell number 6. Now scooch down to cell number 7. It too is negative in gel, antibody test. Cross off all of the antigens that reside on that cell. Scooch down to cell number 8, which is negative in gel, 0. Cross off all the antigens that are presented on that cell. Okay, now the next cell is 2+ in IAT. Ignore that. Go to the next cell that's negative. It's cell number 10. And cross off all the antigens that reside on cell number 10 because you've got no agglutination at IAT and gel. All right? Now, a couple of rules. After you've done this rule out, think which ones are warm and which ones are cold, and that's just something you have to memorize, okay? And we're gonna ignore that for now. What you wanna do is look for, and this is called the 3+3 rule, okay? And I'm gonna give you other rules to include or exclude antibodies. Find 3 tick marks. Let's go down to, look at C, big C. And taking into consideration your negative reactivity in IG, or in gel at IAT. Do you have 3 tick marks? Okay, three cells that you crossed off the big C antigen. Okay. 3+3 rule. If you can find 3 cells that are antigenically positive, but you eliminated those because you had no reactivity in your tube testing or in gel, then you could be 95% sure that this patient does not have an anti-big C. Okay? So if you find 3 cells that were antigenically positive, but because you had no agglutination serologically in your test tubes or in gel, okay, and you've crossed off 3 antigenically positive cells to which you got no reactivity, then you can be statistically 95% sure that you don't have that particular antibody. In this case, 1, 2, 3, 4. Okay, so cell 5, cell 6, cell 7, and 9 were all positive, antigenically positive. I crossed all of those off. Okay, so I can be 95% sure this patient does not have an anti-BC. Okay. Let's look at little e. Cell 5, 6, 7, 8, 9. Okay. All were antigenically positive, but got no reactivity, no glutination in gel. So that's more than 3, right? So I ticked off, starting in cell 5, 5, 6, 7, 8, and 9, all antigenically positive, but I got no glutination. I presented the antigen, but apparently there was no antibody in my patient's plasma to react with the antigens on those cells. So therefore, I can, with a 95% probability, state that my patient does not have an anti-little e. Are you following? Let's look at big S. So cells 5, 7, and 10 were antigenically positive. And again, I got no reactivity in gel. I have 3 tick marks. I crossed off 3 antigens on 3 different cells that were big S positive, antigenically big S positive. So can I, with some degree of certainty, state that my patient does not have an anti-big S? Yes or no? Okay. Look at, let's see. Look at FEB. FYB. WB. FYB. Again, with my native cells. Cell 5, cell 6. Okay. I've crossed off, right? Crossed off the antigens, WB antigens on cell 5 and 6. Do you guys have any additional cells that we were able to eliminate? So I only have 2 cells that are antigenically positive, okay, that are negative. How sure are you that your patient does not have an anti-FEB? So 2 cells that we were able to eliminate.
So not antigen.
We can't really eliminate. Okay, WB still remains, anti-WB still remains a possibility. Okay, you have to keep that in the back of your mind. Are you getting this? Kinda, maybe? Okay, we're gonna do other processes of elimination. This is just one approach. There are other approaches. And I just wanted to give you an idea, I wanted to introduce you to the concept that can we use cells that have been tested by the company for various antigenic makeups. They're indicated positive or negative. And then 2, depending on the types of reactivity we get in the phases of testing we do, we're going to do 2 first. Immediate spin 37Hg. And if any one of those phases are if any one of those phases are positive, then we cannot rule out based on that particular cell. All phases have to be negative
on any one cell for you to use that cell as a rule-out, okay? Meaning you have to have no agglutination with median spin, no agglutination with 37, no agglutination with AHG, okay? And only when a cell is completely negative in all phases can you use it then as a rule-out cell, all right? Ask me questions. Confused? A little bit? There's a lot more to this, we're just getting started. Okay. Well,